Welcome to the Gresty Academy podcast, a crash course in continuous random variables. This is the first video, Introduction to Continuous Random Variables, and we're going to start right at the beginning by describing what continuous random variables are by comparing them and contrasting them with their cousin, the discrete random variable. So basically we have here a dice and we have here a computer. This is a physical dice. Everybody knows it can take the values either 1, 2, 3, 4, 5 or 6. These values here are discrete. It cannot take, for example, the value 3.5. Okay, a continuous random variable. Let's imagine that this is an electronic dice that we have programmed on our computer. It can take any real value between 1 and 6. So the value it could take, for example, is 1.002. It could take 1.0000468. It can take any value it wants between 1 and 6. It is continuous. Okay, that's the first difference between them. Okay, now the second difference is the probability of throwing any one of the values 1, 2, 3, 4, 5 and 6 on a discrete random variable is 1/6 for the dice, but it is not 0. For the electronic dice, the probability of it coming up 1.002 is 0, and the reason why the probability is 0 is because there's an infinite number of real numbers between 1 and 6. It could be 1.0021, 1.0022, 1.002004, or whatever. So the probability of actually getting a specific value on a continuous random variable is 0, which is not the same case as with a discrete random variable. Okay, that's two differences. Something which is the same is the total probability has to add up to 1. Obviously, it has to land on something, unless it lands on a corner, which is highly unlikely. And but likewise, on a continuous random variable, equally, the total probability must equal to 1. And another similarity between discrete random variables and continuous random variables is that the probability must be between 0 and 1. You cannot have a negative probability. So basically, like the discrete, the probability of getting a 1, 2, 3, 4, 5 and 6 cannot be minus 1/6. It's impossible by the definition of probability. And likewise for continuous random variables, the probability of any event has to be between 0 and 1. Okay, so that's the first few things. All right, so now what we're going to do is let's continue here. So we have our dice. What do? Well, we use a probability distribution or mass function to describe our probability. So what I'm going to do here is I'm just going to draw a quick so here is x and here is the probability x equals x, and our probability distribution or mass function is p of x, which we have just agreed is between 0 and 1. So if x is 1, 2, 3, 4, 5 or 6, then the probability of x is a sixth going all the way from 1 to 6, and the sum of all those probabilities is equal to 1. Now on the continuous random variable, we use what's called a probability density function, f of x, where f of x has to be between 0 and 1. For example, our electronic dice, because it can take any value between 1 and 5, it would not be described by the probability distribution function like this. It would be described thus: f of x equals k, and we'll come back to the value of k in a minute, if x is between 1 and 6 or 0 otherwise. That is how we would describe our continuous the probability density function. Okay, and we can draw a nice little graph here of f of x against x, and basically here's the number 1, here's the number 6, and here is the value k, which again we're going to come back to in a minute. Basically the probability is 0 less than 1, the probability is 0 greater than 6, and the probability is k between 1 and 6. And basically this is our probability density function here. Okay, so basically when we look at the sum of the probabilities, the sum of all the probabilities must be equal to 1. So basically on this side, on our random variable, we have the sum between x equals 1 and 6 of all of the probabilities that x equals x is equal to 1. Clearly a 6 add 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 a 6 is equal to 1. On this side, well, we don't use the sum because it's continuous. Instead of sum, we use the integral. So basically on this side, the integral between 1 and 6 of our function dx will equal to 1, and that is equal to the area under the curve. So in the case of our electronic dice, we can now work out what k is, knowing that. So basically we know that the integral between 1 and 6 of our function, which we have agreed here is k, dx equals, well, it equals kx between 1 and 6, and that equals 6k minus k, which is 5k, and we know that that area must equal 1 because the probability must add up to 1, so the area here must be 1. So we know that's 1, so therefore we know that k in this particular case must be 1/5. So if it's not 1/5, then it is not a probability density function because the probability doesn't add up to 1. And by the way, this is actually quite a common question on exams, is that you are given a function, something along the lines of, where is it? Here. Something along those lines of here, and you're asked to find what k is, and the way you find k is basically you have to do the integral and equate it to 1 because the sum of all the probabilities has to be 1. Okay, so that's that. Okay, so now for our, let's have a look at, for our physical dice, the probability, for example, of throwing a 3, well, it equals a 6th, we all know that. The probability of throwing a 3 in our electronic dice, we've discussed, is 0, because it could be 3.00004, 3.002, 3.0765. So the probability of throwing any specific number with an electronic dice or continuous random variable is 0, whereas not the same with a discrete one. The probability here of throwing 3.5 on our dice, our physical dice, well, clearly is equal to 0, and that is actually the same in our electronic dice. Throwing 3.5 is also equal to 0. But more interesting, what about here, the probability of throwing 3 or higher? Well, that clearly equals, if we get a 6th, a 3 or a 4 or a 5 or a 6, and that probability is 2/3 that we get a 3 or higher on our discrete random variable. On our continuous random variables, basically we have to look at the area under our probability density function curve between 3 and 6. That is the probability. We know that the area under the whole curve is 1, so the probability that it's between 3 and 6 is the area between 3 and 6, which means that we have to do our integral between 3 and 6 to find the probability that's a 3 or higher, and obviously we've already worked out now that k is 1/5 dx, and that equals x over 5 between 3 and 6, which equals 6 over 5, take away 3 over 5, which equals 3/5. So the probability on our continuous random variable electronic dice is 3/5 that we get a 3 or higher. The probability on our discrete random variable dice, the physical dice, is 2/3. So they are different. Okay, so let's just do one more here. So the probability, for example, of throwing an odd integer, well, again, that equals a 6th, add a 6th, add a 6th, which is a half. And the probability of throwing an odd integer on our continuous random variable is 0. Again, because there are an infinite number of real numbers between 1 and 6. So the probability that it comes up exactly 1 or exactly 3 or exactly 5 is 0. Okay, so we've done that, and those questions do often come up in exams as well. So what we're going to do now is we're going to finish off this video by looking at expected value of x on discrete and on continuous random variables. So let's go on to a new page here. Okay, so basically we're still on discrete. Right, so the expected value of x for our discrete random variable is equal to the sum of x times by the probability that x equals x. So for our dice, the expected value of x equals, well, it comes up 1 a sixth of the time, and 2 a sixth of the time, and 3 a sixth of the time, and 4 a sixth of the time, and 5 a sixth of the time, and 6 a sixth of the time. So that basically equals 7 over 2, which is 3.5. So the expected value of the throw on a discrete random variable, we would use this formula here, and in the case of the dice, the expected value is 3.5, which of course doesn't have to be one of the values, and obviously in this case it isn't. There isn't a 3.5 here. Let's have a look at our continuous random variable. Let's have a look, because the formula is fairly similar. So the expected value on a continuous is equal to the integral between infinity and minus infinity of x, which is this bit, times by f of x dx, which basically is that bit. So it's the same, except, well, almost the same, except we're using f of x instead of the probability x equals x, and we're using integration instead of summation. So in our e-dice, of course, we don't need to integrate between infinity and minus infinity, because we have already defined, where did we define it here? Outside of 1 and 6, we know that it's 0, so we know the integral will be 0 anyway. So basically, that means, therefore, that our expected value of x on our electronic dice is equal to the integral between 1 and 6 of x times by f of x. Well, f of x, we now know k was 1/5 dx, which equals x squared over 10 between 1 and 6, which equals 36 over 10, take away 1 over 10, which coincidentally just happens to equal the same value. There's absolutely no reason why that should be the case. It just happens to be the case in this particular example. But the way it is worked out is completely differently. But often you do get asked questions on expected values on a continuous random variable, and this is the formula that you use. Now finally, almost always when they ask expected values, what they do then is they ask the variance. So let's just have a quick look at the variance. So on a discrete random variable, the variance is equal to, this is how I remember it, ex squared minus ex squared, i.e. the mean of the squares minus the square of the means. Fortunately, on continuous random variables, the variance formula is exactly the same. So you don't have to remember anything else, which is e of x squared minus e of x squared. So the variance formula is the same. So let's have a look at our physical dice. Now we'll just need to draw our table again. So on the physical dice, we have x is 1, 2, 3, 4, 5, or 6, which means that the probability of x equals x is a sixth, a sixth, a sixth, a sixth, a sixth, and a sixth, which means that x squared is 1, 4, 9, 16, 25, 36. So therefore our e of x squared, which is this first bit here, is equal to 1 add 4 add 9 add 16 add 25 add 36 over 6, which equals 91 over 6. And we've already worked out the expected value of x, which was 3 over 5. Which was 3.5, wasn't it? This one, we already worked that out. So basically, our e of x, we've already worked out, was 7 over 2. So e of x squared is 49 over 4. And therefore, our var, the variance of x for our discrete random variable physical dice, is equal to 91 over 6, take away 49 over 4, which equals 35 over 12. That's how we get the variance of our physical dice. Now let's have a look at how we do the variance of our e-dice, our computer dice, okay? So basically the formula is the same. E of x squared will be the integral between minus infinity and infinity, or in our case, between 1 and 6, of x squared times f of x dx, take away, well, the expected value of x squared, we've already worked out, is 7 over 2 squared. We just worked that out at the top. So all we need to do is another integral here. So basically we need to do that integral, and we've already said that we only need to do it for our dice between 1 and 6 of x squared times a fifth dx, which equals x cubed over 15 between 1 and 6, which equals 216 over 15, take away 1 over 15, which is 215 over 15, which is 43 over 3, and therefore the variance of our dice, our electronic dice, is equal to the square of the mean of the squares, which is 43 over 3, take away the square of the means, which again is 49 over 4, and that equals 25 over 12. Okay, so what we've done in this introductory video, we have, by far the best way I find of understanding continuous random variables is just to compare them with the much more easily understood discrete random variable, i.e. the dice. So we've worked out the differences between them and the similarities. What we're going to do in the next video, we're going to start looking at continuous random variable exam questions, how to ace them, and you will find a lot of the questions, even on very high senior school exams, basically ask questions which test what we have just learnt in this video. Okay, well, I hope you found this useful. If you have, please press the little thumbs up button and subscribe to the Gresty Academy YouTube channel, and look out for the next video in this podcast series. Thank you.